What's up, everybody? Welcome back to Mathletes Corner. It has been so long since we dropped, but we are back here with a banger video as usual. And today we're going to be talking about logarithms. But this is actually a 5 video series. So today's video is just going to be level 1. So we'll really just introduce the idea of logarithms, and then we'll talk about some properties, and then we'll dive into 3 problems. So obviously, first we have to start with our definition. And simply put, our definition is just logarithms are the reverse of exponents. But that definition, at first, it doesn't make a lot of sense, right? So we have this beautifully color-coded exponent form to logarithm form connection, right? So here we have b to the power of c equals x, and that's the form that we're all, at least most of us, are very familiar with, right? But if we were to write this in log form, we would get this expression right here, right? And how we would read this is we would say log base b of x is equal to c. So just to familiarize ourselves with this idea, let's do an example with just numerical values rather than variables. Because of course, when we have variables, it can get a little messy, right? So if we have 3 to the power of 2 equals 9, right? Now, if we were to turn this into logarithmic form, it would be log base 3 of 9 is equal to 2. So when we see this log form, right, we have 3 to the power of 2 is equal to 9. And that's why it's reverse of exponents, right? Because here, 2 is our x value and 9 is our y value, right? But here, our input is 9. So 9 is actually our x value here, and 2 is our y value, which is why these are inverse functions, right? So this whole time we've been talking about how logarithms and exponents are so connected and so similar, and we actually define logarithms using exponents, right? So if we were to observe the properties of logarithms, it would be a crime not to discuss the properties of exponents, right? And I'm talking the basic stuff that most of us already know, right? So let's start with a to the power of 0 is equal to 1, right? How do we write that in logarithm form? Well, that's just the same thing we've been practicing this whole time, right? So it's log base a of 1 is equal to 0. So log base anything of 1 will always be equal to 0. That's a property, right? Now, another thing we know with exponents is a to the power of x times a to the power of y is equal to a to the power of x plus y. So if we were to write this in terms of logarithms, right, that would just be log base a of x plus log base a of y is equal to log base a of xy. And if at first this does not make a whole lot of sense, right? Instead of x, put in a to the power of x. And instead of y, put in a to the power of y. Then what we have becomes way more obvious, right? So log base a of a to the power of x plus log base a of a to the power of y equals log base a of a to the power of x times a to the power of y, but we know that's just a to the power of x plus y from our exponent identity above, right? Now, on the left side, we have x plus y. On the right side, we have x plus y. And wow, they're equal, right? So that's another property. And similarly, if we're doing division, it would be the same thing, but instead of adding, we would subtract, right? So I'll write that property down here too. Let's maybe decrease that font size. So log base a of x over y equals log base a of x minus log base a of y. That's another property. And that is really derived from our property that we just discussed. Now, the two final things that are really important. Log base a of x to the power of r is equal to r times log base a of x. And just as we did with all the other properties, we'll dive into this a little more, right? So say, for example, we had 9 to the power of 3, and we wanted to take that log base 3, right? Well, we know that 9 to the power of 3 is just 3 squared to the power of 3, which is just 3 to the 6th, right? So what we did there is we really took this 3 and we multiplied it by the 2 to get our exponent of 6, right? In the same way, when we do logarithms, we can extract our 3 and kind of do it in a reverse order, right? So if we have 9 to the power of 3, we can take away the 3, leave it out for now, and then just focus on log base 3 of 9, and then we can multiply it by 3 again, right? Which is really similar to what we did here. We took the 9, we turned it into 3 squared, right? We said we'll focus on the 3 later, and we just turned the 9 into our 3 squared. And then the final property is log base b of x over log base b of a is equal to log base a of x, right? And this is such a beautiful property because we can plug in any value for b, and we will always get the same value on the right-hand side, right? B could be 2, b could be 3, b could be 4, b could be anything more than 1, right? And we would still have the same thing on the right-hand side. So those are a lot of properties that we just went over. Now, let's get into some problems. So here we have our first problem. It's the 2010 AMC 12A problem 11, right? So it says the solution of the equation 7 to the power of x plus 7 is equal to 8 to the power of x can be expressed in the form x is equal to log base b of 7 to the power of 7. And we want to find the value of b, right? So the first thing we notice is this 7 to the power of x plus 7. And we remember that x plus 7 in the exponent from somewhere else, right? When we have that addition sign in the exponent, we always want to split it. So we'll take 7 to the power of x times 7 to the power of 7. And here we see that 7 to the power of 7 right here is also in our formula for x that we want to get, right? So that gives us a hint that we're going in the right direction. Now, as given in the problem, we know that this is equal to 8 to the power of x, right? Now, because we notice the 7 to the power of 7 is common between these two places, we want to isolate it on its own. So if we isolate that, we get 7 to the power of 7 equals 8 to the power of x over 7 to the power of x. And this is just equal to 8 over 7 to the power of x. Now we go back to the problem, and we see that x is log base b of 7 to the 7. So that basically means that b to the power of x is equal to 7 to the 7. And that's exactly what we have right here, right? It's exactly what we have there. So b is just equal to 8 over 7, and that is option C. So the big idea there was finding that 7 to the power of 7 and then isolating it. And then from there, it was just a simple conversion from exponent form into log form and vice versa. So here we have our next problem, the 2015 AMC 12B problem 8. And it's just evaluating this weird expression that we're given, right? So first thing we notice is we have 625 and we do have a log 5. So let's try to take 625 and extract the 5 out of there, right? So if we have 625, we know we can just write that as 5 to the power of 4. And that 4 is really convenient because we actually have this 1 over 4 in the exponent. So let's rewrite the expression, but instead of 625, we'll put in 5 to the power of 4 and see what happens. So 5 to the power of 4 to the power of log base 5 of 2015 to the power of 1 over 4. And obviously, when we have something like this, we can just multiply all of the exponents through, and we'll notice that the 4 and the 1/4 will cancel, and we'll be left with 5 to the power of log base 5 of 2015. And this is not necessarily an expression that we've seen before. So let's just focus on that exponent because that's the funky thing, right? If we had an integer exponent, it would be done, right? So let's focus on that exponent. Let's say x is equal to log base 5 of 2015. And since logarithms are new to us, let's just convert it into exponent form. It's more convenient. 5 to the power of x is equal to 2015, right? Now we look back at the expression we want to find, and we say if this is x, if log base 5 of 2015 is x, then what we want is just 5 to the power of x. So we look back here, and we see 5 to the power of x is just 2015. So we go back to the question, and we see 2015 is option D. We can choose that and move on. So this opens up the light to another property that we haven't discussed, actually. So let's just get this here. B to the power of log base b of a will always be equal to a. And if you think about it, it actually makes sense because of the way that we define logarithms to be the reverse of exponents, right? Like if you take two inverse functions, you take one value, plug it into one of the functions, take the output and plug it into the other function, you'll go back to where you started, right? It's the same idea because exponents and logarithms are inverse functions. So with that being said, move on to the next question. This is the 2018 AMC 12B problem 7, and again, we have to evaluate this funky looking expression, and that's pretty complicated. So just as a small hint to get us started, let's think about that last property that we discussed in the beginning, right? So we said log base b of x over log base b of a is equal to log base a of x, right? Now what can we do? Well, what if we canceled out the fraction, or in other words, got rid of the fraction on the left-hand side, right? So we'll multiply both sides by log base b of a. We get log base b of x is equal to log base b of a times log base a of x. And again, this is such a beautiful property because we can kind of chain the a's together and we can kind of cancel them out in a sense, right? So if we have log base b of a and log base a of x, we can kind of combine them together to get this new log base b of x, right? And when we look back into the problem, we actually noticed that, like in log base 3 of 7 and log base 7 of 11, if we were to multiply those, we would get log base 3 of 11 because we're combining those two values. And now it gives us a hint to how we can proceed with the problem. So just to make it a little more clear, let me write it in this way. Log base 5 of 9, log base 7 of 11, log base 9 of 13, and so on and so forth until our second to last term is log base 21 of 25. And that would actually be on this side. And then finally, the final term is log base 23 of 27. So first we can multiply the left side and then the right side, and then we'll put them together. Okay, so now we have a plan and we can move forward with that. So as we said before, we can take log base 3 of 7 and log base 7 of 11, combine them to get log base 3 of 11, right? And then if we keep going, it'll be log base 3 of 11, log base 3 of 15, log base 3 of 19, log base 3 of 23, and then we'll finally get log base 3 of 27. And that is super convenient because what is log base 3 of 27? That's just 3, right? Because 3 to the power of 3 is 27. And on the right side, it's super similar. In the end, we'll get log base 5 of 25. And we already know that's just 2. So if we multiply 3 and 2, that gives us our final answer of 6. And we're done. So that's all for this video. Thank you for watching. Don't forget to hit that like and subscribe button. And we'll see you next time here at Mathletes Corner.